Hello, welcome back to Chapter 5, Section 3, Solving Quadratic Equations by Graphing and Factoring. In this example, we're going to be dealing with two special types of factoring. Both of them you've seen in Algebra 1. I believe it's Chapter 8, Section 5, or Section 6, one of those, if you were in St. Paul schools when you took Algebra 1. However, even if you weren't in St. Paul schools, I'm sure that you've seen these. But we're just going to review it a little bit. Both of these factoring methods actually have names. However, you can still factor these the old standby. What two numbers multiply to give this, add to give that, the middle term. All right? And when I talk about that, we're talking about things that look like this. X squared plus b times x plus c. So what we're saying is what two numbers multiply to give the c but add to give the b. Okay, so one of the factoring skills we're going to be dealing with is called the difference of two squares. That's where I got a plus b times a minus b, and that looks like a squared subtract b squared, the difference of two squares. And if we look at this, if I multiply to show what happens, if I do a plus b times a minus b, a times a is a squared, a times negative b is negative a times b times b is positive a times b, and then b times negative b is negative b squared. This one and that one have a sum of 0. They're opposites of each other. So a plus b times a minus b equals a squared, this one, subtract b squared, that one. Now how is that going to show up in the factoring that we're going to be seeing? So you're going to see examples like this. X squared subtract 9 equals 0. Hopefully that's not one of them that I picked. Nope. And we're going to be able to factor. We'll say, okay, I know that something squared subtracts something squared. I can split it this way. So this is x squared subtract 3 squared. So this will be x plus 3 times x minus 3. And of course, then we can finish solving it from there. You can also look at it this way. What two numbers multiply to give negative 9 and add to give 0? Because that middle term is 0. Well, that'd be 3 and negative 3. All right, we can do that. The other pattern that we're going to see are called perfect square trinomials. And these are all the same idea. So I got a plus b, a plus b. And this one is going to be a minus b, a minus b. So this is if everything's added, this is if both of them are subtraction, and this is if you got adding and subtraction together. So these are all together. Look what happens here. I get a to the second power, a times b again, and b to the second power. So that gives me a squared plus 2 times a times b plus b squared. So I'm going to be looking for patterns where the first part is something squared, like x squared. And then I'm going to see the last thing will be something like a perfect square, like 16. And then in the middle, I'll have something like 8 times x. So this would be x plus 4 times x plus 4. If it's subtracting, I get a squared, I get negative a times b, and b squared. That's the same as that, except instead of positive 2ab, I get negative 2ab. So it'd be, you're going to see factoring like this, x squared subtract 10x plus 25. So what and let me finish that. That'd be x subtract 5 times x subtract 5. So what we're going to be looking for will be perfect squares. Perfect squares are numbers, whole numbers that I get from squaring, basically counting numbers, whole numbers. So 1 to the second power is 1, 2 to the second power is 4, 3 to the second power is 9, etc. So the perfect squares would be 1, 4, 9, 16, 25, 36, 49, 80, sorry, I'll skip one, 64, 81, and 100 for the first 10. And then, of course, there's more. There's an infinite number. I'm not going to be able to list them all. So it'd be very, 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 very useful for you to make a list of your perfect squares, and we'll talk about this live in class, to make a list of the perfect squares so that you can recognize them right away. This is everything we're going to do. We can factor just using our previous method, but it's just a little bit shorter if I recognize that I have perfect squares. Let's do a couple of examples. And there's one other thing we want to talk about here with this one. We've made the transition now from finding the zeros of the function to finding what we call the roots of the equation. So they are very, very much related, but they are not the same. And they're related almost to the point to where a lot of people like mush them together in their thinking, and that's usually perfectly okay. There was an example where when I was in a class when I was at River Falls, it was a more complicated problem, but I was asking my instructor, Dr. Leek, great guy by the way, if he's still there at River Falls, if you have him. And I asked him for some suggestions for how to like solve a complicated equation, and he said, "Well, just graph it." And it's funny because I had like separated in my mind that those were, like two different skills, and it was kind of clear that it was like, no, you can interchange from one to the other. They are different, but they are very, very closely related. So I'll keep mentioning that and bring that up as we do the rest of chapter 5, and probably even a little bit further than that. Okay. In this case, notice, unlike the previous examples we've been dealing with, I don't have f of x equals. None of these are functions. However, I can set them equal to 0, which is kind of like the middle ground. When you saw the problems before, and let me pull out the previous paper, like this one. We did this before. What did we do? We set this equal to 0. At this point we have an equation. This is no longer a function. This is a function. But what I did was I let this function equal 0 to find what we call the zeros. Well, now we're just skipping all that. We're just going straight to the equation. And I know that that's a little confusing, so please ask questions if that doesn't make sense. The skills are going to be very, very similar though. I'm going to do something so that I have my equation equal to 0. In this case, I'm going to add -1 to both sides. And I get 9x to the second power, subtract 1 equals 0. Now I need to factor this. I have a 9 in front of here. That's a perfect square. I have a subtraction. That's a difference. And I have a 1. That's a perfect square. So this is the difference of two squares. So the square root of 9 is going to be 3. So I get 3x plus 1, and I get 3x subtract 1, and that equals 0. So I factored this by the difference of two squares. And again, you can do this the traditional way. Since I have a coefficient on the x squared, I have to do the factoring where the first term, the first coefficient, is something other than 1. And there's a method for doing that. Okay? But again, that's Algebra 1 stuff. But this falls on, we're talking about the difference of two squares here, so I'm going to do this method. I'm not finished. I have to do 3x plus 1 equals 0, or 3x minus 1 equals 0. And I'm only going to skip some of the things I need you to show just because I'm running out of room. I'm going to subtract 1 from both sides. I get 3x equals -1, and then I divide by 3, I get x equals -1/3. Over here, if I add 1 to both sides, I get 3x equals +1, and that tells me x equals +1/3. So those are my two roots of that equation. Both of these, -1/3 and +1/3, when I square it or take it to the second power is going to give me 1/9. A negative times negative is a positive. If I do 9 times 1/9, I get 1. And that one, actually, we're going to learn about problems like this in the next section, where we could actually solve this by square roots. And we'll talk about when you do which one as we go. All right. Let's talk about this one. First of all, I'm going to move everything to the same side. I'm going to put that 40x over here, and I'm going to put it in standard form. So you get 0 equals 8x squared, subtract 40x, plus 50. All right, now I'm looking at this problem and I'm thinking, all right, it's not the difference of two squares, because I don't have squares here at all. I have a subtraction, and the difference of two squares always have two terms. This one has 3. Maybe this is a perfect square, but I don't have perfect squares. Sorry, I'm starting to get the hiccups. But okay, I got 8 and I got 50. What do I have here? Oh, 8 and negative 40 and 50 are they all have a common factor. That common factor is 2. This is 2 times 4. This is 2 times negative 20. This is 2 times 25. And that 4 that I mentioned, that 25, those are my perfect squares. So I'm going to divide everything by 2. And 2 is my common factor. I know everything's going to be divisible by 2. I get 0, because 0 divided by 2 is 0. 4x squared, subtract 10x, plus 25. 4 is a perfect square. 25 is a perfect square. The square root of 4 is 2. The square root of 25 is 5. What's 2 times 5? 10. And of course, because it's negative, that means I'm going to subtract it. So this is 0 equals 2x subtract 5 squared, which means 2x subtract 5 times 2x times itself, 2x subtract 5. So 2x subtract 5 equals 0. Add 5 to both sides, I get 2x equals 5. Divide by 2, and I get x equals 5 halves. Now, notice that for the first time we've been doing these, I only got one answer. This is what we call a multiplicity. If I can write that all right here. The multiplicity means I actually got this answer twice. So we're going to talk about this throughout chapter 5. And I'm going to be bringing it up a lot. But when you find the roots of an equation, roots of a quadratic equation, or the zeros of a quadratic function, you're always going to get 2 answers. For all the problems we've done so far, we always got 2. This is the first time I only got 1. But the reason why is because this was actually 2x minus 5 times 2x minus 5. So what I got was 5 over 2 for both of them. And that's called the multiplicity. That idea will be coming up a lot. And when it does, I will bring it up to you. And we're going to tie it all together as we go. All right, let's do this one. I'm going to add 4 to both sides. So I get x squared, subtract 4x, plus 4 equals 0. Now I mentioned this, you can always factor by the tried and true method. What two numbers multiply to give positive 4, but add to give negative 4. Notice that this is a perfect square, and so is that. So again, this is a perfect square trinomial. This is going to be, and I'll write it this way, x subtract 2 times x subtract 2 equals 0. Or you can say x subtract 2 squared equals 0. So again, I'm going to get x subtract 2 equals 0, add 2, and I get x equals 2. And again, I keep saying again, I don't know. X equals 2 here, x equals 2 here. I get x equals 2 twice. So it's a multiplicity. Last one in this section, 25x squared equals 9. Just like this one right here, I'm going to add negative 9 to both sides, and get 25x squared subtract 9 equals 0. So difference of two squares for these two, perfect square trinomials for these two. Make sure you recognize. And notice that had a term with an x, that had a term with an x. These two don't. So take your time and look at them carefully so you know what the differences are. The square root of 25 is 5, the square root of 9 is 3. So this is 5x plus 3 times 5x minus 3. And unlike the other times, that plus and that negative, that addition and that subtraction, that means these are not the same. Last time I could write it like that because they were exactly the same. Both of the factors were exactly the same. These are different. Very, very, very similar, except one's adding, one's subtracting. So now I have to do 2. I get 5x plus 3 equals 0. Subtract 3 from both sides. 5x equals negative 3. Divide by 5. X equals negative 3 divided by 5, or negative 3/5. The other one's going to be positive 3/5. 5x minus 3 equals 0. Add 3 to both sides. Divide by 5, and I get positive 3/5. So these are not the same. They are opposites of each other, which is going to happen when I have a difference of two squares. Okay, we'll have lots of examples of that when we get to it. Good luck.